So the goal of this course really is to fully understand all of these four equations, which govern how electric and magnetic fields work. But in order to understand these equations, we really need to understand what on earth these little upside down triangles mean and all of this stuff. So we first have to take a little break to brush up on our math. In this class, we will be using a right-handed coordinate system, not a left-handed coordinate system. So the way you know whether it's a right-handed coordinate system is what you want to do is you want to take your right hand and point your fingers along the direction of the x-axis, and then point your thumb in the direction of the z-axis. And basically your open palm here should be facing the y-axis there. I'm sketching it out because I tried to do this with my hand and it was like really awkward. So anyhow, always go with the right-handed coordinate system. Let's talk about vectors. Every vector has a magnitude, it has a direction, and it has a position that we specify with a position vector here. So here we've got our vector A there, and it's at a point P, and we describe that point P with this vector here that goes from the origin to the point in question. For example, suppose we have an electric field with -2 x in the x hat direction, 1 in the y hat direction, and 6 in the z hat direction. And it's at this following point with the x, y, and z coordinates here. What we could just say is that the electric field at that point, instead of actually just listing these numbers out, we can just describe it with a position vector, which would be 2x hat plus y hat plus 6 z hat. And there in your textbook, the notation they use is like OP for the position vector for point P. So you can also use that notation as well. In this course, we will be using 3 different coordinate systems, and the type that we use will depend on the problem. The coordinate system that we are currently have been using is the Cartesian coordinate system, where you just have x hat, y hat, z hat. And one thing I want to point out about the Cartesian coordinate system is that if you have a vector A at some point P, and it's in this direction here, and then you start changing P, or you move it around, the orientation or direction of that vector A will stay the same. And it doesn't matter what point it's at, that basic direction is the same. And you will find that that's actually not necessarily the case with the other coordinate systems. All right, let's talk about the cylindrical coordinate system. So unlike the Cartesian coordinate system, where you designate a point by just specifying x, y, and z components, with the cylindrical coordinate system, you specify a point P in space with a distance r here, lying in the xy plane, an angle phi here, which can be from 0 to all the way to 2 pi, and a height or distance z here. So that's how you specify the point. And then the unit vectors that we use to designate a vector at a given point is we have r hat, so basically a vector going out in the direction of this, in the xy plane in the direction of r here. And then we have phi hat, which goes tangent to this circle here, which is in the xy plane. And then we also have z hat, which goes up. So the unit vectors here are not necessarily aligned with the x, y, and z unit vectors that we were working with originally. Now, here's one thing that's interesting about the cylindrical coordinate system is that the position vector, a position vector for point P, so this, we could say this is OP here, we designate that with a vector here where you have basically a distance r in the r hat direction, as well as a distance z in the z hat direction. Now, you might be tempted to also include this, phi hat. That is not correct. The reason is because when you're dealing with unit vectors is all about specifying a distance, not an angle. So you can't multiply an angle times a unit vector, which is about distance. So that does not work. So actually, when you want to specify the location of a point, you can specify the position vector with this here, but you also need to specify phi to know exactly where the point is. Another thing I want to mention about the Cartesian coordinate system is that if you have a vector A here with certain, a hat or AR, A phi, and AZ components, the orientation in three-dimensional space of that vector A is actually dependent on its location in space. And the reason has to do with how these unit vectors work here. So like, for example, this unit vector in the r hat direction, depending on the location of the point here, so r hat is pointing this direction if the point is over here. But for example, if we chose this point here, then r hat is actually in that direction, the opposite direction as was what it is here. So when you're actually specifying a vector there, the actual orientation of the vector in three-dimensional space will depend on precisely where its location is. It's unlike the Cartesian coordinate system where you have a certain vector that has ax, ay, and az components, and it's oriented in a certain way. No matter what point you choose, it's just fixed. Here, it's different. If you change a different point, it'll go around and like point in another direction. Same thing happens with phi hat here. So depending, here at this point, the unit vector phi hat is oriented in this direction at this point we've drawn here. But if you picked a point like over here, well then the vector, tangent to the circle would be phi hat. Well, now it's oriented in a different direction. It's oriented in this direction instead of this direction. So the orientation of the vector actually depends on your location in space, and that's one of the different things about about the cylindrical coordinate system.
You mean what? You look like an egg, or like a little loaf. Are you a loaf? A bread loaf?
All right, let's talk about the spherical coordinate system. In the spherical coordinate system, we designate a point in space by specifying a distance from the origin, or r, an elevation angle theta, and an azimuth angle phi. So phi can be from 0 to 2 pi, and theta can be from 0 to pi. And these are our unit vectors here. So we have a unit vector r hat along this r arrow right here, going radially outward. And then we have theta hat, which basically is perpendicular to r hat and lies in the same plane where this angle theta is being measured. And then you have phi hat, which lies in lies parallel to the xy plane and is tangent to this circle here that lies in the xy plane. So then you can specify your vector A there with those different components. Now, like the cylindrical coordinate system, the position vector here only includes one component here. You cannot do something like theta hat plus phi hat. That doesn't work because again, those are angles. So you can specify a distance here with your position vector, but you also, to fully designate where the point is, you have to also designate a certain value for theta and phi. So that's important. Another thing I want to mention is, just like the cylindrical coordinate system, the direction of a vector A will depend on the location in space. So notice how if you vary theta and phi, the orientation of your unit vectors will change. If you change phi, then this will go from being oriented this way to being oriented over here as you change phi. So your unit vectors, theta hat and phi hat, will change as you vary theta and phi. The only thing that doesn't change is if you, for example, kept the same theta and phi value, but you changed your r value, then your unit vectors, the orientation of your unit vectors stays the same if you vary r. So it depends mainly on theta and phi. So that's just something to be aware of.